There are four important types of problems in organic chemistry, in my opinion. We've already tackled mechanism, predicting the products, and structure determination, and now we look at the fourth important problem, which is multi-step organic synthesis. So the goal of this unit for this series of lessons is to learn how to be able to synthesize large and complex molecules from small and simple starting materials. And this is done every day by chemists working in the pharmaceutical industry. So let's start with an example that I am very familiar with. This molecule is a compound that I have synthesized in the course of my research, and in fact, I have the world supply of it in my research lab. It is a 14-carbon molecule that also has 13 hydrogens, 5 nitrogens, and 4 oxygens. And it has a molecular weight of 315. So this molecule is a drug that, well, a molecule that we have tested as a drug active against cancer. So it is this proper size, shape, and number of functional groups of a typical drug molecule. So now the question is, how do I make this, and what are my starting materials? Well, I gave you some hints by the color coding in this structure. So the molecule is made from 4 smaller pieces that are linked together using 3 chemical reactions. Okay, so we have a red piece, a green piece, a yellow piece, and a blue piece. I'm not going to name all of these structures for you, but what you should note is depicted below here are the actual starting materials that I used in the synthesis of this compound. Okay, so the red piece, we're only going to count the non-hydrogen atoms here. The red piece contributes 5 of the carbons and 2 of the nitrogens of what ends up in the final structure. The green piece contributes 2 carbons and 1 oxygen into the final structure. The yellow piece contributes 2 nitrogens, and the blue piece contributes 7 carbons, 1 nitrogen, and 3 oxygens. Okay, so what you should notice is that there are some extra functional groups present in the starting materials that do not make it into the final product. Specifically, there is an extra aldehyde in the green piece, and there is an extra aldehyde in the blue piece. So this is a common theme when thinking about these problems. So far, functional groups have been something you've had to memorize, and you've had to use them in structure determination problems. But now you're going to see why these groups are actually called functional groups, because they are the places at which we form bonds when we're trying to put together larger and more complex structures from simpler starting materials. So the strategy of synthesis is to think backwards. So when you're given a target molecule, what you need to do is mentally dissect it into pieces, just like we did on the last slide. What starts out as a fairly complex 14-carbon molecule, we see comes together into 4 smaller fragments. Chemists have a fancy word for this. It is called retrosynthetic analysis. And the systematic way of thinking about synthesis problems like this, starting at the end and thinking backwards, was the intellectual contribution of a chemist from Harvard named E.J. Corey, who won the 1990 Nobel Prize in Chemistry for his major accomplishments in organic synthesis, but also for the retrosynthetic analysis method of thinking about a synthesis problem. So once you have mentally dissected it, you can then decide which bonds you're able to form using chemical reactions and which reactions you will use to form them. Then you write down the exact starting materials that you will use for each reaction, and then finally repeat this process until all of your starting materials fit the constraints of the problem. So if you're thinking backwards and you have a 14-carbon molecule, you may break it up into 2 7-carbon molecules, But if you're told that you have to start with starting materials of 4 carbons or less, each of those 7 carbon fragments is going to have to be treated as a target molecule, and the same process done on each of those until you get into the smaller fragments that you're allowed to use. So what should be clear to you from this introduction is that being able to solve synthesis problems involves having enough reactions in your toolbox to use. If I asked you to come up with a solution to the synthesis problem that I gave you on the last slide, so far you would not be able to do that because you have not learned the reactions that you will need to learn to solve that problem. You will actually learn those reactions later on in the second semester of organic chemistry. But for the moment, we need to look at a simpler problem, because right now we only know 2 organic reactions: substitution and elimination. In this unit, we're going to add 2 more important classes of reactions. So we can't really do a problem that's interesting yet. We have to add carbonyl addition and oxidation and reduction reactions as they apply to organic molecules, which is very different from the way you treat oxidation and reduction in general chemistry. And then finally, the other big piece that we're going to cover in this unit is we're going to focus on methods for forming carbon-carbon bonds. So a problem that you will be able to solve at the end of the unit is the following: being able to prepare this 14-carbon tertiary alcohol from starting materials that are 6 carbons or less. So if you do the math quickly, a successful solution will involve forming 2 carbon-carbon bonds. Okay, if you have to get up to 14, you could have a 6 plus 6 plus 2, 6 plus 5 plus 3, but you are not allowed to start with a 7-carbon fragment. And if you look carefully at this structure, the molecule actually divides itself up into 3 very obvious fragments. But we'll get to that more in the course of this unit. Before we could even think about how to solve this problem, we have to think about how we form bonds. Okay, I alluded to this on the first slide that we need the functional groups to help us. But the way we form a bond in general is that we react a nucleophile with a carbon atom that contains a good leaving group. So an example that we can do right now based on the chemistry that we've learned previously is to synthesize this following molecule. It's a secondary amine from starting materials containing 3 carbons or less. So since there are 6 carbons and a nitrogen, but there's only 6 carbons in this molecule, we can carry out this synthesis in what we call one step, meaning that we only have to form 1 bond. So which bond do we form? Well, the answer is that we want to form one of the carbon-nitrogen bonds, because as you know, nitrogen is a good nucleophile. It has a lone pair on it, so those are rather obvious bonds to be able to form using a nucleophilic substitution reaction. Okay, so for this particular molecule, we're going to want to use the SN2 reaction rather than the SN1 reaction. If you're doing substitution, in general, SN2 is more useful than SN1 because SN1, as you learned, frequently competes with E1 elimination. So there are 2 possible solutions here because there are 2 carbon-nitrogen bonds. We can start with isopropyl amine and react that with propyl bromide, or we can start with isopropyl bromide and react it with propyl amine. Either reaction would work in principle, but the first one would work better because SN2 reactions are faster with primary alkyl halides than they are with secondary alkyl halides. So remember, does your final product have a bromine in it? No. There are functional groups present in your starting materials that are not present in the products. because if you did not have that bromine there, if you just had propane, which is what a lot of students like to do on these problems, there is no leaving group. So if you're going to have the nucleophile come in, it's got to displace a leaving group, and of course if something is a leaving group, it's going to leave and not be present in the final product. Okay, so that's the overview. In the next lesson, we will actually focus on how you form carbon-carbon bonds and looking at carbon electrons.